Good day everyone. Today me and my team will be presenting the project presentation of the subject additive manufacturing. So my name is Tan Lek Wee, followed by my member SENG, Som Tien Sun, and HANGEL ANAK ERIK. Now proceed to the introduction. So firstly, our project product will be motorcycle swing arm. So in our aim, we aim to topology study optimization on the swing arm. Number 2, we aim to ensure the functionality of the swing arm. And thirdly, we aim the parts consolidation on swing arm. And then the objective is created to achieve the aim. So firstly, we have to investigate the effect of topology study on the swing arm. And secondly, we have to analyze the FEA results of swing arm for before and after topology study. And later, we have to validate the effectiveness of the modified swing arm to ensure the functionality of the swing arm. And for the next part, which is the literature review, I will pass it to my group member HANGEL ANAK ERIK to present his part. Thank you.
My name is HANGEL ANAK ERIK. Today I will talk about topology study and optimization. First is topology in 3D modeling. It is referred to as distribution and structure of 3D model. It consists of two types, which is 4-side polygon and 3-sided polygon. Next is topology optimization. It's used to optimize and reduce layout of a material for a given design without reducing its performance. To maximize the performance of the design, we can change load, boundary condition, and constraint. This is the literature finding. Wang et al. Has do FEA analysis and topology automation on this support structure. They find that mass of the support structure decreased from 48 kg to 28 kg, and material removal rate of the support structure is 80%. Mera et al. Also had control topology optimization and weight reduction on this automotive part. They find that weight reduced from 2.2 to 1.52 kg, and the part has been redesigned again. This is the original part and then redesigned to this one. After optimization, the stiffness and the strength of the part improve. Mira and Chauhan has research on clamp cylinder. This clamp cylinder has gone to FEA analysis and topology optimization. The weight of the clamp cylinder decreased. Principle of maximum stress increase. Total deformation value increase, and stronger and lighter clamp cylinder has been met. This is the picture of principle of maximum stress on modified clamp cylinder model. That's all for me. Thank you.
Hi, I'm Tan Lek Wee and I will be presenting the methodology. So firstly, we can see here we have to choose a product and identify its technical and economic reasons in manufacturing that product. Then after that, we will proceed to reverse engineering on the chosen product. And later, we will perform the first FEA analysis on the original 3D model, which is before modification. And later, we perform a topology study on the original 3D model. Then, we will perform the modification after the topology study, which is then we also will base on the topology results. And after that, we perform again on the FEA analysis on the modified product. And from the analysis, we can achieve equivalent stresses and also safety or factor value. And if the safety factor value is satisfied, we can proceed to discussion and conclusion. If the safety factor value is not satisfied, then we perform again the topology study until we achieve a satisfied factor of safety. And now I'll be presenting also the element of our methodology. So first element is reverse engineering. Reverse engineering is basically deconstruct a product in order to achieve its design information. So firstly, we measure our swing arm by using measurement tool, such as vernier caliper, measuring tape, and even a ruler. And later we build a 3D model by using manual hand sketching and also 3D CAD drawing. And later The second element is meshing. So in meshing, we'll be using triangular and curvature base mesh at mesh element size of minimum 0.6 mm and maximum of 3 mm. In order for us to check on the mesh quality, we have to calculate the Jacobian value. So as we know that the acceptable Jacobian value benchmark at lower than 40. So we have to achieve at least a Jacobian value lower than 40 in order for the product to be acceptable. So we calculate the Jacobian value using feature known as mesh quality plot in SolidWorks software. And later during topology study, we create the mesh also with triangular and curvature mesh with mesh element size of 1 mm and maximum at 5 mm. And now we proceed to the third element of methodology, which is finite element analysis. It is a method for us to get the vorticity stress and also factor of safety value. And the figure below here is the boundary condition of our swing arm. So firstly, we can see the force apply condition at total of 2000 Newton on both sides, which means by one side is 1000. And at the green arrow side here is the fixed geometry. So we assume that the bolts lock at here and also the axial support of the rear wheel is fixed at here. And now we proceed to the fourth element of the methodology, which is the topology study on swing arm. So at the figure below here show that the preserved area for our topology study. And we set the preserved area depth at 5 mm. And our goal is to achieve a mass reduction of 50%. And to keep also the base stiffness and the factor of safety larger than 1. And now, which is the last element of a methodology, is modification. So firstly, we have to modify based on the topology study results. And during the modification, the rough surface will be formed because the mesh reduction process is based on the mesh element. And later, the topology study model is displayed as design guidance. So we go to the view settings and select simulation display in order to display on the topology study model. Then we select the most material side as the design guidance in order to modify the swing arm. There is features known as extrude cut, which we use to remove the unnecessary part. And we also apply the fillet on thin part to reduce the material. And that's all for me for the methodology. For the next part results, I'll be pass it to my group member SENG to present his part. Thank you.
My name is SENG and this is the result and discussion. First of all, the model looks like this, the original swing arm, and then the topology optimized swing arm, and the redesigned swing arm looks like this. For the reverse engineering, sketches is made from the original swing arm. So this is the sketches looks like, and we draw it using SolidWorks, and this is the drawings in the SolidWorks. For the mass properties of original swing arm, it has a original mass of 6.3 kg. And then to ensure the functionality of the original swing arm, we done FEA analysis on the original swing arm. This is the mesh details. This is the mesh plot, how the mesh looks like on the original swing arm. The minimum element size is 0.6, maximum element size is 3, total nodes is 400k, total number of elements is 300k plus, and the Jacobian ratio is 6.575. For the stress analysis, the maximum stress is 98 megapascal, and the factor of safety is 2.2. For the topology study of original swing arm, the mesh detail, this is the mesh plot looks like. The minimum element size is 1 mm, maximum element size is 5 mm, total nodes is 111k, total element is 70k, and the Jacobian ratio is 6.412. So for the goal and constraint we set in the topology study, The goal type is best stiffness to the weight ratio. The constraint type is the mass constraint, where we need to reduce the mass by 50%. We set it in the SolidWorks topology simulation. And then we also set preserved region in the study. So this diagram shows the preserved region with a purple color, and the preserved depth is set as the 5 mm. So during the topology study, this area will be preserved and not to be removed by the topology optimization. In the topology study, this is the convergence of the result. The mass target is 3.16, which is the 50% of the original mass. So the simulation will run at a number of iterations until the mass reach the target. As we can see here, the number of iterations stop at 37, which means the mass converge at the iteration of 37. For the best stiffness, it converges at the number iteration of 4, and it follows the simulation until it reaches the iteration of 37. This diagram shows the topology optimized model, where the calculated element mass is the 2.8 kg. After that, the model is redesigned based on the topology optimized model, and this is the mass properties of the redesigned swing arm. The mass for this redesigned swing arm is 3.6 kg, and then to ensure the functionality of this redesigned swing arm, we conduct the FEA analysis, and this is the result. For the mesh detail, this is the mesh plot. The minimum element size is 1 mm, maximum element size is 5 mm. Total nodes is 270K. Total element is 172K. And the Jacobian ratio is 20.73. Notice that the Jacobian ratio is more than 10, which indicates the mesh quality is not good. As we see in this figure, the Jacobian ratio is 20.73, but compared to the whole model, most part in the model has blue color, which has a low Jacobian ratio. Only a few small dots on the model has higher Jacobian ratio. So we assume that this mesh still has a good quality and the result is still reliable. Besides that, the Jacobian ratio of 20.73 is still within the benchmark of 40. Thus, the Jacobian ratio is accepted. And then this is the FEA analysis of the redesigned swing arm to check its functionality. The maximum stress is 98.55 megapascal and the factor of safety value is 2.2. At last, we compare the original and the redesigned swing arm. The stress values only varies a little bit, but they still have the same factor of safety value, and the mass for original swing arm is 6.3 kg. For the redesigned swing arm, the mass is 3.6 kg. So in conclusion, there is a mass reduction of 42%, which is conducted and optimized by the topology study, and the part consolidation is also achieved, which will reduce the part count to 1. As before, the part for the original swing arm is welded by a few parts, but as we conduct the production of the redesigned swing arm using additive manufacturing, it reduced the part count to 1.
As conclusion, the aim of this project have been done, which the mass of final design of swing arm have been reduced by 42% and achieve a good stiffness to weight ratio. Besides, the part consolidation also achieved, with the part count have been reduced to 1 after redesign of swing arm. The reverse engineering is done to the original swing arm. Figure above show the hand sketch of original swing arm. All the measurement is measured by ruler, manual caliper, protector, and so on. After that, we have drawn it using SolidWorks. Figure below show the detailed drawing of
original swing arm. After draw in SolidWorks, the Jacobi ratio have been used to measure the mesh quality of swing arm. The Jacobi ratio of original and after topology optimization swing arm got below 10 means it have good mesh quality. For the final design of swing arm, the maximum Jacobi ratio is 20.73. Due to it may consist only small part and it did not exceed the band value of 14, so we assume this mesh quality can be accepted. Before start the topology optimization, 16 faces of the swing arm have been set as the preserver region, which shown as the purple color of the figure above. This is because the part need to connect to motorcycle using the bolt and nut, so we cannot change the geometry of this part. Figure below show the result after topology optimization. The yellow color is the part that must be kept, and the blue color region represents the part that can be removed. Due to the safety factor after topology optimization, with 15% is less than 1, so we change a bit design of the swing arm. Figure below show the final design of swing arm with a safety factor of 2.2 and mass reduction of 42% compared to the original swing arm. For the recommendation, the software specialized for smoother the topology optimized surface can be used to redesign the optimized model, as it will not add much material to smother the surface, so the mass of redesigned swing arm can become lower. That's all for our presentation. Thank you.